The extended Kalman filter is derived from the general sequential probabilistic inference steps by making two critical assumptions in different places in the algorithm. The first assumption has to do with when we're computing the estimate of an output of a nonlinear function, and this includes the state estimate in step 1a and the output estimate in step 1c. The extended Kalman filter at those points assumes that we can approximate the expected value of some nonlinear function of x, the state, by reversing those operations and computing the function of the expected value of that state. Mathematically speaking, this is not true. It is true if the function is linear, but otherwise it is not true. The approximation may be reasonably good when the function is fairly linear, but if the function is very nonlinear with discontinuities and all kinds of curvature and everything like that, this approximation is not a very good one. But in any case, this is what the EKF does, and we'll see its performance later on. And then at different places in the algorithm, when we're computing the covariance estimates at the output of some nonlinear function, the EKF uses a Taylor series expansion to linearize the system equations around that operating point, and it throws away the higher order terms. So we keep only the linear terms in the expansion. And again, this approximation is not going to be perfect. If the system dynamics are in fact linear, the EKF is doing exactly the right thing, and both of these cases, if the system is linear, will produce exactly the same results as the linear Kalman filter. But when the system is nonlinear, this is one generalization that is not exact, but it can give good results. In this section, we're going to show how to apply these two different approximations or assumptions to derive the extended Kalman filter equations from the general 6 probabilistic inference steps. Starting with step 1a, when we predict the state, the general solution says we need to compute that. Now this is a challenge because now f is a general nonlinear thing. We're not putting any restrictions on what f might be any longer. And the expected value of a nonlinear thing would require integrating over all the probability density functions and so forth to be able to compute it. And that's almost never computable in any kind of a closed form or reasonable simple algorithm. So instead, using assumption 1a, the first assumption, we are going to switch the order of these things. So instead of finding the expected value of a function of x, we're finding a function of the expected value of x. So the expected value of x given all previous y is what we called the estimate of the state at the previous time step. The deterministic input is propagated through, and the expected value of the noise, the process noise, is also used as an input. The process noise might have a zero mean. We do assume that it's a completely uncorrelated white signal, but possibly with a non-zero mean. Again, what are we trying to do? We're trying to use our best estimate, or our best guess of what the state was in the previous time step, which is this, to find the best prediction of the state right now. And EKF says, well, just propagate the estimate through the state equation and you'll get the state prediction. Now this is not optimum, but it can be okay. Step 1b says I want to find sigma x tilde minus. I want to find the covariance of this prediction error. So first we figure out, well, we say that's expected value of x tilde k minus transpose. So I have to figure out what is x tilde k minus, and by definition it is that. And xk, using the state equation, we can write as this. and x hat k minus from step 1a we write as that. And we're left with the challenge of trying to subtract two general nonlinear functions from each other and get something reasonable, and furthermore compute this in a closed form solution. I can't do this in an algorithm as is because I don't know what x is and I don't know what w is. Those are unmeasured. So whatever I simplify this down to has to operate only with knowledge of x and w bar and the covariance of x and w and stuff from before. So what EKF does is it says, I am going to approximate that term using a Taylor series expansion. And Taylor series expansion says some general function at x plus x, no, I don't do it that way. Say at x naught plus delta x is equal to f of x naught plus partial derivative of f, actually total derivative f x naught with respect to x naught. Let me write that more carefully. Partial derivative evaluated at x equals x naught times x minus, or times delta x actually, etc., with higher order derivatives and so forth. So you can look that up in your math book to double check, but we're going to do that with this first term on the next page. So xk, we're saying, is going to be approximately equal to, because we're going to be truncating this infinite series expansion, we're not keeping all of it, we're going to say it's approximately equal to the f evaluated at the set point, and we're choosing the set point to be the input x variable equal to x hat k minus 1 plus, and the input w variable equal to w bar, and then plus the derivative of the function with respect to the first variable times evaluated at the first variable equal to that input times first variable minus that value. And then we could do second order, third order, etc. expansions on that first input variable, but we're truncating it, so we don't. And then we could do the derivatives with respect to the second variable, but those get multiplied by 0 because I know the second variable u is deterministic. And then finally the third variable here, derivative of f with respect to w, evaluated at w equals w bar, multiplied by w minus w bar. That's what our x is. And when I substitute that in, so this here gets replaced by all of this other stuff. Notice that this term is going to completely cancel that term, and that's the reason we chose the particular linearization set point that we did, was to make that constant disappear. And I'm left with, when I do the subtraction, of x tilde being what is left here, which are these things. That's x tilde. The first derivative in this expression we call a hat k minus 1. Second we call b hat k minus 1. And this gives us that x tilde minus is a hat times x tilde k minus 1 plus, and then plus b hat times w tilde. So we have an expression for the estimation error. I'm going to use this now to find the covariance of the prediction. Covariance of the prediction error. So sigma is equal to expected value of x tilde transpose. And plugging this in, we've seen this enough times that I don't put all the steps in any longer. When you FOIL that out, the first terms and the last terms are retained, but the inner-outer terms are not, because we're assuming that this and this are uncorrelated with each other, and when we do the subtractions we get zero mean out, so they go away. So that gives us an expression here. This is how we compute the covariance of the prediction error. I caution you that the A hat and the B hat matrices are found by a total differential solution, not by a partial differential solution. And we're going to go through the algebra or calculus carefully here to see how the two are related. And in this case, we'll find out that they amount to the same thing. And so in certain literature, you will see the partial derivative being used instead of the total derivative. However, it's most accurately the total derivative, and the reason I stress that is because next chapter, when we're looking at state of health estimation and we use a common filter to help with that, it will make a difference. The two will not be the same, and if you use the partial derivative, it won't work, and if you use the total derivative, it will. We need to compute the derivatives of f with respect to its input arguments. And by the chain rule of total differentials says the total differential of f is equal to the partial of f with respect to first input times the total differential of the first input plus the partial of f with respect to the second input times the total of the second input plus partial with respect to third times the total of the third. The partial derivative says how much does the functional output change if I change a specific input like this one and leave all other inputs constant, the same, unchanged. So that's why it's partial. It's the partial change due to changing one variable. The total derivative says how much does the output change if I change that one input, but maybe that one input indirectly affects another input, which affects another input. So there's kind of a chain of causality. By changing one thing, I'm really changing many things, and the total derivative says what's the total effect of all of that instead of just the one-by-one effect. And so that's why we're looking at, well, how much changes if I change x and nothing else, by how much x is changed, and how much do I change if I change u and nothing else, multiplied by how much u changes, and how much if I change w and nothing else, and then by how much w changes. We get, for example, df by dx by dividing both sides of this equation by dx. So I divide by dx, divide by dx, divide by dx, which is what we've done in this next line here. So df by dx equals partial f by partial x, because those d's cancel, they're the same thing. And then in the next line, the du by dx, you have to think about that and say, oh, the input u is deterministic. It's not a function of the state of the system in any way, unless perhaps you had a feedback control system attached. But this here, we're looking at the open loop system, so no. U doesn't change when x changes. U changes for whatever other reason. So that there is 0. And then I have a dw by dx for the final term there. So going through, W is this process noise, and we can argue that the state of the system has no impact on the process noise either. It's not a causative impact, so that's 0 and that's 0, so those are wiped out. And in the end, we get df by dx equals partial f by partial x. So I could have used either notation in this case, except the total derivative is more correct. Go through the same argument to find df by dw, and it's the same as partial f by partial w. And we have then how to compute our A matrix, A hat matrix, and our B hat matrix. In order to go any farther in the derivation, we would have to know what f was, and knowing what f is, we can do the derivative and find the matrices, but without knowing the function itself, we can't go further than this at the moment. So we proceed to step 1c, where we look at the output prediction, really. And the system output, according to the probabilistic inference step, says I want to find the expected value of the output equation. And again, we employ the first assumption where we swap the order of these and say this is approximately equal to the output equation evaluated at the expected state. And the expected state is going to be x hat k minus. And the expected sensor noise is going to be v bar. So similar to step 1a, we assume that to get this nonlinear output prediction, the assumption says that we should propagate the best known inputs through this function to get the outputs, and that's going to give us our result. Now we move on to step 2a, and in step 2a, remember LK equals sigma x tilde y tilde, and then multiplied by sigma y tilde inverse, if memory serves. So I'm going to have to find, I already have an x tilde, but I need to find a corresponding y tilde. And we use a similar approach. So y tilde equals y minus y hat, which is the true output minus the predicted output. And we use a Taylor series expansion on the true output part around the equilibrium point x at k minus uk v bar k. And that gives us yk is about equal to h of x hat plus dh by dx, evaluated at x equals x hat times x minus x hat, and etc. Down here, similar thing with v. Exactly the same idea as we encountered in step 1b, just used in a different context here in step 2a. This cancels that exactly. No, it doesn't. It cancels that exactly. So I'm left with the remainder as this being my y tilde equals everything inside that loop. The derivatives, we can go through the partial derivative, total derivative. Computations, again, we find out in this case they are the same also. And we could basically FOIL everything out inside of expectations to find the expected value of y tilde transpose, or sigma y tilde would give us this, and sigma x tilde y tilde gives us, after a few lines of math, it gives us that right there. And we combine all of that together to get the Kalman gain, and so we have L equals sigma x tilde minus from step 1b times c hat transpose, where c hat is this partial derivative evaluated at x equals x minus. And then all of that multiplying the inverse of c hat times sigma x times c hat transpose plus d hat times sigma v times d hat transpose, where d hat is all of that. It's the partial of the output equation with respect to the sensor noise input evaluated at the expected sensor noise input level. That is our Kalman gain. It has almost exactly the same form as the linear Kalman gain, except there's c hats instead of c's, because this is the linearized C matrix, if you will, at this point in time, and it has d hats as scaling on noise, because I'm not simply adding noise. So the original output equation had y equals cx plus du plus 1 times v. Here I've got a d hat times v, and that location there, it's the scaling of the noise. So I've got d hat times sigma v times d hat transpose, where you could, I guess, have argued that originally in the linear I had I times sigma v times I transpose over there. So this is a reasonable generalization of the linear Kalman filter steps, as we can see. The step 2b says take the prediction, take the measurement, take the predicted measurement, take the Kalman gain, combine them in this way. That gives you an estimate. This step is the same for every kind of Kalman filter. No changes whatsoever. And then lastly, we look at the error covariance measurement update. And once again, this is the same for every kind of Kalman filter with no changes there whatsoever. So out of the 6 steps, 2 of them have stayed unchanged, and 4 of them have had some modification to them. The modifications have been due to either assuming that the expected value of a function of x is about the same as a function of expected value of x, that happens in 2 steps, and or saying that we can find the covariance by doing a nonlinear Taylor series expansion of a nonlinearity and then chopping it off. Those are why those 4 steps changed. So that's the introduction. We're going to next move on to an example of the EKF, including some code to implement an EKF, and we'll see that it's really not much different from a linear Kalman filter, and it's not that difficult to implement.